upper tail at that value is equivalent to area A. So it's not that difficult because, okay, I'll show you, actually I already showed you last time in terms of table, right? So you can see that in this table, the area is marked by the symbol alpha, right? And you can see here that alpha is the subscript of this chi-square value. So you can see that you have like variable like 0.995, so that corresponding to an area here that is equal to 99.5%. And once you know, right, when you know what size of the area you want to look for, the other parameter is just degree of freedom. So you're going to be given like say degree of freedom at 4, so they're going to be this row. And then the area will be, let's say, 95%. So it will be that column. So you can see that the intersection between the column and the row will be 0.710721. So that will be your chi-square value that you want. So it's not that difficult from the table, and that is what we want to do, right? We want for you to be able to identify the value. Okay. However, you can see that in my table, I have two chi-square table. One, you can see that the probability is about like above 90%. The second one, right? If you go to the second table, this is when the value that it start from 10% and then keep decreasing 5%, 2.5%, 1%, and 0.5%. And that because usually sometimes we want to find a chi-square value that corresponding to the upper tail of the distribution and the lower tail of the distribution as well, right? So that's why we have that two tables. So, but it's not difficult, right? Let me explain what this means. What do I mean by that? Okay. Let me use, I think drawing a graph is better. Okay, so let's say if I want to be able to identify two chi-square value, right? So chi-square value gonna start from 0, right? So that is chi-square on the horizontal line. It's gonna be value of the chi-square, and the top will be probability of that chi-square, right? Or f, function f. Okay, that's f. So let's say I want to find 2 points. One is A and one is B. The connection between these 2 points is that I want the area here to be 1% and that area to be 1% as well. Okay? So let's say I give you like degree of freedom at, let's say degree of freedom is 5. Okay, so if you given degree of freedom, you given the area, right? I want the area in the upper tail to be 1% and lower tail to be the 1% as well. So you have to be able to look at the table and tell me what would be A and B. So for this side, right, you can read off the table because the table always tell you the upper tail, the area in the upper tail given the value. So you just look at 1% and then you can read off B from the table. So let's look at that. Okay, so I'm going to have to use this, the second table, right? So I want 1%, so that will be my 1% column, right? 0.01, so that 1%. And degree of freedom is 5, so the value will be this one, 15.0863. So that I can read off the table. But what about this value here, right? What is A? Now the table only tell the upper, tell the area, the chi-square value of the upper tail area. But if the left hand side, the lower tail is 1%, it means that this, okay, so I highlight with red, including the tail here. If that is 1%, the red area here will be 99%. So when I want the probability of the lower tail to be 1%, it means that I have to look from the table, but from the 99%. Because the table only tell you the probability, the area to the left, to the right hand side, upper tail. So you have to calculate that area and then look in the table for that value. So if we go back to our table, right? So we have to go to the first table of chi-square, because that's when we find all the area that have 99 or above 90. Right? So 99 is this is 99%, this column, and degree of freedom is 5, so it's 0.5543 and then 00, this number. Okay, so it's not difficult. It's just that if you want the lower tail area, you have to be able to calculate the complement of that area, right? If you want 5% on the lower tail, it has to be 95%. If you want let's say if you want, like, this one is extreme, so if you want 0.5% in the lower tail, upper tail will be 99.5%, so it will be that column. Okay. So you can look in the table and then you can put the answers. So here A will be 0.5543 and B will be 15. You can see that this is what we expect, because B has to be greater than A, and you can see that A here is like very close to 0, whereas B is quite big, it's 15. Okay, so that, as long as you can look from the table and then give me that answers, then you should be okay. Okay, any question? Okay, let's look at another sample. Okay, so this is a sample in a PowerPoint presentation. Okay, so say that we started to find a point in a chi-square distribution with n degree of freedom, such that the area to the right, the upper tail, is 5% or 0.05. So you can, again, you look into the second table, right? So look at the column where the probability of area is 5%, and you know the degree of freedom is 8, so 15.5073, that would be your chi-square value that corresponding to this graph. So this point will be that 15, right? 15.5073. Yeah. And if we were to use, right, the code for R, every time that you want a value for a given probability, you have to use the Q prefix. So this Q chi-square, you want 0.05, degree of freedom is 8, and you want the area in the upper tail, so the lower dot tail have to be false. This one you don't have to specify, that is default. So you can see that we have the same number as in the table. On the other hand, if you want, as I show you, the area in the lower tail, right? Here I said that find a point in a chi-square distribution with any degree of freedom, but the area to the left, right, to the left is 0.05. So as I told you, if you want the blue area to be 5%, so it means that the space, the gray space under the curve here is 95%. So that is when you have to go and look on the table where the column is 95%. And the degree of freedom is 8, so it means the value is 2.73 to 64. So not any, I don't think it's that difficult. Right? If you want, again, so here, there are more than one way, right, to specify this. You can, if you want lower dot tail, right, to be so if you want lower dot tail to be false, it means that you calculate the upper tail. So the probability here have to be 0.95, have to be 95%. But here we can, because in R, you can calculate upper tail or lower tail, unlike the table where it only tell you the upper tail area. So here you can see that we can specify 0.05 that we want the blue area, and we want the lower tail, right? The area to the left, so lower dot tail have to be true, and the degree of freedom is 8, and you can see that you get the same number, 2.732. So it's the same, that is the same number as in this graph, this table. So together, what we try to achieve here is this. We try to calculate the chi-square value that have 5% in the lower tail and 5% in the upper tail. And you can see that this chi-square 2.73 is less than that, because that is in the upper tail, so it's like higher than this. And if you cannot have a negative chi-square value, because chi-square value is always positive. Okay, any question? Okay, so the last one that we look from the table is the chi-square distribution. F distribution. So last time we explained the connection between the Z distribution, T distribution, and the chi-square distribution, right? So Z distribution is standard normal, and usually we use it to test the sample mean, right? The test sample mean, the distribution of sample mean. For chi-square is like for testing of variance, when you want to estimate the variance. F distribution is when you want to test the ratio of two variances. So you have two populations, and you want to see whether these two or maybe two samples from the two populations have the same variance or not. So that is when you have F distribution. So F distribution actually is a ratio of two. S symbol here is it stands for sample variance, right, that we use in chi-square distribution. So it's a ratio of two variances, and then we have F. So since the variance have the chi-square distribution, so F distribution is actually the ratio of two chi-square distribution. So you can see that all like four distributions, Z, T, chi-square, and F, they're actually related to one another. Right? F distribution is ratio of two chi-square distribution. And that creates a problem because when you have one chi-square, you have 1 degree of freedom. When you have two chi-square distribution dividing one another, so it means that you're going to have 2 degrees of freedom. You can have a degree of freedom of the top chi-square distribution and the bottom chi-square distribution. So the top we call it numerator and the bottom is called denominator. So we can have a degree of freedom in the numerator on the top of the ratio and the degree of freedom of the denominator or the bottom of the ratio. The distribution is like that, and we all know now that distribution of t chi-square and f, they have like very complicated functions, and we're not going to try to integrate that, right? That's why we have the table or the program R to calculate. So we still use the symbol nu, right? But now we have nu 1 and nu 2. Nu 1 is the degree of freedom of the numerator or the top one, and nu 2 is the degree of freedom of the denominator or the one in the bottom of the ratio. So now when you look at the F distribution table, you're going to have 2 degrees of freedom. Let me show you. Okay, let me show you by look at the table. Okay, this is chi-square. Chi-square and t both have 1 degree of freedom. But when you look at the F is table 7. Okay, this is F. You can see that because the ratio of chi-square is look like a chi-square distribution, and the value is start from 0 as well. Right? So you can see in this table that you have the numerator degree of freedom on the top, right? Till you each column, and then you have denominator degree of freedom on the left, right? So this means that this information, right, this first set of information have different numerator degree of freedom, but the denominator degree of freedom is always 1. Okay. And alpha tell you the area again in the upper tail. So this is 10%, 5%, 2.5%, 1%, and 0.5%. So once you know what area you want, you know the numerator and denominator degree of freedoms, then you can have a look on this table. So we have there are different type of table for F distribution. This one is quite good, it's quite succinct, but still we're gonna have a lot of table. So you can see that now in terms of numerator, I go up to 9, right? And in terms of denominator, I go to 7. So second table, here is when numerator is start now 10 to something like 120 or infinity, and degree of freedom of the denominator is still from 1 to 7, right? And if you want the degree of freedom of denominator to be more than 7, so you have to look at another table. So you can see that now we have more than 2 tables for F distribution. Actually more than 2 tables. You can see that now the numerator is still 10 to 120, but degree of freedom on the denominator is start from 8 to 14. If you want more than 14, again, is another table. So you can see that for F distribution, the fact that you have 2 degrees of freedom, it complicates the table. You need more than 2 tables. Actually, this is like 6 or 8 tables in total. And still, if you want degree of freedom like 35, you don't have it here. So that's why it's easier to know functions to calculate this value using R, because you can specify any numerator degree of freedom or denominator degree of freedom, or any probability as well, the area. Here we fix it to only 10, 5, 2.5, 1, and 0.5. So it's quite limited. So if in the final exam, right, you see the paper of the final exam is quite thick, then you can guess that I actually included F table or F table in it because you're gonna need a lot of F table if we keep like changing the degree of freedom. But if I fix to only just less than 10 degree of freedom, I think like 1 or 2 F table should be okay. Right? But anyway, let's see. Right? How? Oh, not this one. Okay. So the mean of the F, the expectation is nu2 divided by nu2 minus 2. Right? And the variance, this form, right? We're not going to use it here. The main thing again is for you to be able to look at the table and then try to identify the F value associated with it. So here you can see that it like the chi-square distribution we just have now. Sometimes you ask to calculate this area to the right and or maybe like the area to the left in the lower tail, right? You sometimes we have to do both. However, unlike chi-square, they don't have because the table is already a lot. So you can see that we strict to just the area of 10%, 5%, or less than 10%. So we don't have like chi-square where we have like 99% or 95%. But there will be a formula for you to calculate that. Okay, let's see. So here, what is the value for F, right, of F distribution for 5%, right? And like in the picture, so 5% in the upper tail of the distribution, where the numerator degree of freedom is 3 and the denominator degree of freedom is 7. So to combine all of that, I want F 0.05, 5%, comma. The first one is the numerator degree of freedom, 3, and the second one is the denominator degree of freedom, 7. So I have to look at this table, right? This is the first table actually, and you want the numerator degree of freedom to be 3 and the denominator to be 7. Okay, so it has to be from this last section of the table, but then I also specify that I want 5%, so you can just look on the row of 5% and you can see that it's 4.35. It's as simple as that. So the answer is 4.35. Okay, and now you can see that if you're using R, it's going to be QF. Again, Q is for to calculate the probability. F is for F distribution, and you can see that I use 0.05. The first argument here is the numerator, degree of freedom 3, denominator, degree of freedom 7, and we want lower tail to be false because we want upper tail to be 5%. So you can see that we get the same number as we have looked in the table. So this is not difficult, right, for F distribution on the upper tail of the distribution. But now, if you want the area under the curve in the lower tail, right, that is quite difficult because the table that we have do not tell that area. Okay, but there is a way. There is a way to calculate that from the table that we have. For example, if we want, okay, let me give you a specific example. So suppose that this is F distribution, right? And if you want 5% on the upper tail, that is easy. You can read off the table. But if you want, like, let's say that this is F2, this is F1. If you want F1 such that the area to the left or the lower tail to be 5%, right? Usually in the chi-square distribution, we're gonna look for the red area, because that 5%, the red area including the tail, have to be 95%. However, in the F, we do not have that table, because if we have the table for 95%, we're gonna have to like double the amount of table that we already have, right? But we can, right, use this formula, F of 1 minus A of nu 1, so that is degree of freedom 1 and 2. That is equivalent to 1 over F of just A, and now you have switched nu 2 to the front and nu 1 to the back. Okay. So let's say that we want, right? Let's say that the nu 1 and nu 2, nu 1, like in the example we see, is degree of freedom of the numerator is 3 and nu 2 is 7, right? So what we want is, we want 95%. So this number, right, we want it to be 95% or 0.95. Right? So, but then if 0.95 equal to 1 minus A, so it's implied that A is 0.05 or 5%. Right? So it means that FA here is 0.05. So when you want the numerator degree of freedom to be 3 and that to be 7, so you have to reverse it. So you have to put nu 2 in front, 7 and 3. So if, right, this means that you have to go to look in the table for F of 5%, and where is the first position is numerator degree of freedom is 7 and the denominator degree of freedom is 3, and then you substitute that into this formula, 1 divided by this number, and it's going to give you the F of 95% divided at 3. The first degree of freedom is 3 and the denominator degree of freedom is 7. So that is a formula that you can use to find these answers. Okay. So let me show you that. Okay. So we're going to use this example. So you can see that in my PowerPoint, right? So I want the area in the upper tail to be 95%, and I want the numerator degree of freedom to be 3, denominator to be 7. So what I have to do is, I have to find the reverse of it, which is 1 divided by F at 5%, and the first numerator degree of freedom is 7, and denominator is 3, right? So you can look at this table. You can look at, even though that we want originally we want 3 to be the numerator degree of freedom, but because we have to use this formula, so we have reversed it. So now we look at the numerator degree of freedom at 7, right? And then the denominator degree of freedom at 3. So it's going to be, again, this section of the whole distribution. And then we want it 5%, so it means that the number that we want is 8.89. Okay? So what you have to do is 8.89, plug it into this formula, so it's going to be 1 over 8.89, and you get 0.11248594. So we can use this formula to find an F statistic or F value when the area is more than, well, not 10, 5 or 2.5%, but something that like 95, 90 or 97.5%. Now, to show that this formula is working, you can see that now I can use, because in R, you don't have to bother with the formula, you can just QF, you want 95, right, to be the upper tail, right, so the lower tail has to be false. Numerator degree of freedom is 3, denominator is 7, and you can see that when you plug it in, you get this number and it's the same as the above. It's slightly different, but if you round the above number up, right? So this is 1125, that is 11248. So when you round it up, it's about the same number. So that's it. That is how you can use F table, right, to calculate the statistics, the F statistics. So in step 2, you're going to use this table and this value to do hypothesis testing. But because hypothesis testing, well, we already have a lot to learn, right, after the midterm, so it's not included in here. Any question? Okay, not difficult, right? Okay, so this is the last topic I want to cover, right? I don't know how far I can go, but I already uploaded the PowerPoint into the Google Classroom, so it's about sampling distribution. Okay. So if you open, it's already that sampling distribution. So I sort of shorten it. But for me, this is the most important chapter. This is the basic of what you have to do next. Okay, we have about 40 minutes to do. Okay, let's see how far I can go. So, what is sampling distribution? What are you going to learn, right? This is accumulation of everything we have learned so far, and we're going to study about sampling distribution of the sample mean, just the sample mean, okay? And if you understand, this will be the basic of statistic theory that you're going to use. So we study about discrete distribution, continuous distribution, but what is sampling distribution? A sampling distribution is created by, as the name suggests, sampling. Okay? And the method we will employ, that we're going to study, we will employ the rules of probability and the law of expected value. We're not going to go into details of the form in terms of like derivation of the formula, but we're gonna try to understand the area. So try to understand the concept. Right? Okay, let me try to explain this. So the idea is that we have a population, right? But we cannot obtain the data from the population because it's too big, right? Think of population of Thailand, 75%, let's say like 70 million people now. So we cannot collect data from all of them, right? So I told the story to the second year student that's studying with me that how many? Okay, just to collect, right? Just to collect about 8,000 questionnaire, right? So if you're gonna collect data, it means you have to go out and you have to interview people. And we have 75 million people in Thailand, 65 million or 70 million people in Thailand. So that's going to be a lot of work. If you would like to talk to everybody and just like 5,000, if you interview like 5,000 people or 8,000 people, usually that's going to be, the company that doing that going to charge about 2 million baht or maybe 5 million baht at least, just to collect data from 8,000 or 5,000 people. So if you're gonna collect from all of them, from all the population in Thailand, that would be, we're talking about like more than 100 million baht for the cost of doing it. So normally you don't do it, it's too big. So what you do is, usually you just collect sample. Right? Let's say the sample is size n. It could be like 500, 5,000, 70,000. So what we want to know is that if we do that, how accurate our analysis is going to be, right? So, okay. So you can see, have a look at this, right? So in our example, we're gonna focus on sample mean, right? So imagine that we have population, right? And you draw a sample. You can see that now I have 1, 2, 3, 4 sample, right? Usually you draw just one sample, but imagine you draw a sample, because if you draw like by random from the population, so the distribution of sample within the sample and the distribution in the population should be the same, right? But then, let's say if we're interested in sample mean, right? We would like to know what is the population mean in the population, but we cannot collect data from the population. So what we do is we draw a sample and then we calculate the sample mean, okay? So you can see that what I write down here is a sample statistic, right? So it means that we use data in the sample to calculate some sample statistic. For example, sample mean. So if I draw 4 sample and then I calculate, I'm gonna have 4 sample means, right? So if I keep drawing more sample, let's say I draw like 100 sample. Each sample, I can calculate the sample means. So I'm gonna have 100 value of sample mean. Clearly, these different value of sample means is a type of random variable. And the distribution of it is called sampling distribution. And the question is, what is this distribution? This is a distribution that caused by keep sampling from the population. But what we want to know, right? What we want to know is whether this distribution going to be the same as the distribution in the sample and in the population or not. And the answer is that no. Okay? So let's say that, like I said, we want to know the population mean. And let's say the population mean is 10 in the population, but I don't know. I don't know that it's 10, right? Because in order to know, I have to know all the data in the population. Now, what I can do is I can collect the sample and then I calculate the sample mean, right? Even though like the population mean is 10, but because I collect only 500 observation, so my sample mean should not be the same as 10, right? It could be something close to, right? 11, for example, the sample mean is 11. I collect another sample, and the sample mean is 13. Collect another sample, and sample mean is 9. And collect another sample, the sample mean is 8.5. Now, these, right? Okay, let me ask you this. Is this a random variable? The population mean that equal to 10. Is this a random variable? The answer is no. This is a fixed, a constant value. If we know all the data in the population, we can calculate that number, but we don't know, right? So it's not a random variable. This, however, the sample mean is a random variable because every time we draw a sample and when we calculate the sample mean, it's going to be different. Should not be the same. It could be the same sometime, but most of the time it's not. This means that the value is keep changing depending on the sample that we collect. So when the population mean or mu is not a random variable, y bar is a random variable. So when you have a random variable, it must have a distribution. What I want to show you here today is that the sampling distribution of the sample mean is in fact normal distribution. Right? It doesn't matter whether what is the distribution of the population. The population could have, say, exponential distribution. So when you draw a sample, the sample gonna have exponential distribution as well. But when you calculate the statistic, it's gonna have a normal distribution. That is why normal distribution is so important, because population can have any distribution. The sample gonna be, this gonna have the same distribution, right? Because you just draw a sample from the population. But whatever statistic you calculate from the sample, it's gonna have a normal distribution. And I can use computer to show you that. Okay, so y bar is a random variable, and it can be proved that the sampling distribution is normal. And this is a theory that we call central limit theorem, or in short, CLT. Okay. So the whole all the topic after the midterm is for you to understand about central limit theorem. Okay. So I'm gonna give you an example, right? So I'm gonna use the distribution in the population that's so far removed from the normal as much as I can. And that is, let's say that what we're interested in the population is the distribution of throwing a dice. Okay, this is the first distribution we studied, one of the first, and this is what how we're gonna show it, right? So you know from the beginning, right, that if you throw a dice, so it's gonna turn out 1, 2, 3, 4, 5, 6 with the equal probability, okay, 1/6. And we have calculated the mean already, right? The mean, because it's discrete, that means just a sum, no integration, sum of y multiplied with the probability. And it is 3.5. The variance, right? So again, no integration now, just a sum of y minus mu square weighted by probability, and that is 2.92. And the standard deviation is square root of the variance, which is 1.71, right? Okay, so this is a code, right, that we have been using the sample, right? X is 1 to 6, so that there are 6 outcomes, and I generate the sample size to be 100,000. So dice is a draw, it's like a draw by throwing a dice 100,000 times. And you can see that the mean is 3.5, 0 something, and standard deviation is 1.707, so it's about 1.71. So you can see that my simulation of a dice, throwing a dice 100,000 times is the same, right, at this number. The mean is 3. The population mean, here is the population mean is 3.5, and the standard deviation, population standard deviation is 1.71. So this simulation is show the same as what we expect from the math that we have. Now, okay, and the distribution, I plot the distribution of that simulation of throw a dice 100,000 times. You can see that, well, what we should expect, right? We expect that the graph will be only 1, 2, 3, 4, 5, 6, and the height should be about the same because the probability of it happening is 1/6 in theory. Okay. Now I want to know that the population mean mu of 3.5 is not even an actual outcome. The outcome can be 1, 2, 3, 4, 5, 6, but the population mean is 3.5. Okay. Now, so I try to summarize what we have been doing. So the population distribution now is throwing a dice. What is the mean? 3.5 population mean, and standard deviation is 1.71. So the distribution of the population is like this. It's discrete, right? Now, let's assume that we draw a sample and then we calculate the sample mean. What I want to show you is that even though in the population is something like discrete probability distribution, but if we calculate the sample mean, the distribution of sample mean will become normal distribution according to the central limit theorem. Okay. So now suppose that how do we draw a sample? So here I'm gonna each of my sample gonna have only 2 observations. So basically what I do is that I'm gonna roll a dice 2 times, get my value like y1 and y2, and then to calculate the sample mean, I add them together and divide it by 2, and that will be my sample mean. So I'm gonna keep doing this 100 again, another 100,000 times, and I'm gonna keep the record of my y bar, and then I'm gonna plot my y bar to you. Okay. In terms of y, right? Y can be only 1, 2, 3, 4, 5, 6. So y1, y2 here is the outcome from the first roll of the dice and the outcome of the second roll. It has to be either 1, 2, 3, 4, 5, 6. But once you calculate the sample mean, right? The outcome change. It can be more than 1, 2, 3, 4, 5, 6. Let me show you what it is. Okay, let me. Let me show you the code first. I set up C. So I want me like to be able to reproduce the same outcome as again. So I set the seed number to be 1, 2, 3, 4. Right. So the first is nothing. It's just like define a new variable dice, and again the outcome can be 1 to 6. Then the size is 2 because we say that we're gonna throw a dice 2 times. Okay. So once you use that function and you try to see what dice here is 4 and 2. So the first row is 4, the second row is 2. So when you calculate the sample mean, 4 plus 2 is 6. 6 divided by the number of observation 2 is 3. So you can see that the mean of the dice is 3, right? So now I want it to be shorter, but again I set the seed number to be the same. So I should have the same outcome, random outcome. So you can see that I use the same code as above, sample, right? 1 to 6, size is 2. But now, I calculate the mean straight away. So I combine like this line and this line together, create the mean straight away, and then I define that to be y bar. So you can see that one is use this code and see what my y bar is 3, right? So it's the same. So whether you're using these two lines or just combine it into one line, it gives you the same y bar. What I want to do here is that you can see, right? So I'm using replicating as well, again. So now I want to do it 100 times. First start with 100 times, right? Each time you throw 2 dice, you calculate sample mean, and then you do it again, and repeat it 100 times. So you can see that in my even B, what I have is I have 100 value of sample mean, right? So 5.5 here is the sample mean of my first experiment. 2.5 is the outcome, the sample mean of my second experiment. What you see here is that even though like the outcome of the dice is 1, 2, 3, 4, 5, 6, but the sample mean from that can be more than 6 outcome, 1, 2, 3, 4, 5, 6. It could be 5.5, 2.5, 4.5, right? But it seemed to be like, even though it more than 6 outcome, but it's still like, you see a pattern, right? So what I'm doing now is that I use the same code again, but now I do 100,000 times. So you can see that when you throw 2 dice, the outcome can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are only 11 outcomes that is possible. Either 1, 1.5, 2, 2.5, 3, 3.5, and 6. But you can see that I use function table, right? So from 100,000 times, what I found is that I have 1, right? I found sample mean of 1, only 2,703. 1.5, 5,617. And you can see that I keep finding more often, right? 2 is more often than 1.5. 3, 2.5 more often than 2. 3 is more often than 2.5. The most often number I found is 3.5. I find 16,717, right? And then 4, it keeps decreasing. 4.5 decreasing. So you can see that the most often number I found is at the population mean. And then it keeps decreasing on 2 sides. Why is that? It's because of this. Look at this. So it's easier to show you that when you throw the dice only 2 times, right? So when you throw a dice 2 times, there are 36 possible outcomes. You can see that this, right? 1, 1, 1, 2, 1, 3. The first column telling you like the possible 36 outcome of throwing 2 dice. What is the second column? The second column tells us what is the sample mean if you observe 1, 1, 1, 2, 1, 3. So that this is the sample mean from these 36 possible outcomes. You can see that, right? The only way that I can observe sample mean of 1 is only when the both dices have to turn 1 and 1. That is the only one time that I can calculate sample mean of 1. So that is highly unlikely. Same as 6, right? The only time that I can calculate sample mean of 6 is when both dices turn out 6. Again, highly unlikely. So that's why, right, I only observe 1, 2,700 times, and 6, 2,761 times. But you can see my red circle, right? this red circle is a combination of outcomes that have the same mean, which is 3.5, right? If I have 1, 6, 3.5, the mean is 3.5. 2, 5, right? 2 plus 5, 7, divided by 2, 3.5. 3 and 4, also 3.5. 4 and 3, 3.5. So you can see that out of the 36 possible outcomes, 6 of them gonna give me sample mean of 3.5. The most frequent possible sample mean. So if you plot the graph, you can see that I'm gonna have something like this, right? The highest possible value is in the middle at 3.5, and then it dies down, and it looks like a normal distribution. So we start the population with just throwing a dice, 1, 2, 3, 4, 5, 6, but the distribution of the sample mean is something already look like a normal distribution. So this is only when you have 2 observations. What about if I increasing the observation? Okay, you can see that now from the sample mean, I find the mean of the sample mean. I got 3.5, but the standard deviation is not 1.71. Okay, we talk about that later. Now, this is when, right, I increase the replication to be 100,000. Sorry, it's the same 100,000, but the sample size to be 15. So before, I only throw the dice 2 times, so I collect the observation only 2 times, and then I calculate the sample means, right? Now, we increase the number of observations, so instead of throw the dice 2 times, we throw the dice 15 times and then find the sample mean. So these are the possible value now that you throw the die 15 times. You can see that the possible value increasing from before, right? And if you plot the graph, it really now look like a normal distribution. So when you increase the number of observations that you collect, before you calculate the sample means, the more the distribution of y bar will get close to the normal distribution. And this is called central limit theorem. Okay, as this is important. So as n increases, the sampling distribution becomes more like the normal distribution. Okay? With big enough n, right? With big enough n, we can, because it's normal distribution, in order to see the probability of normal distribution, you can use a SAT table. So this is a powerful tool in statistics because it doesn't matter what population you're interested in. It doesn't matter what distribution of the population, but if you calculate something like a sample mean, it always have a normal distribution. So that's why we call it normal distribution, because normal means it's likely to happen, right? If you say like normal Thai people have the height of 170, so it means that a height of 170 centimeters is the most often in the population. So what we call something, when we call something normal, it means that it happens a lot. And we call it normal distribution because it's happened a lot. If you calculate some statistic from a sample, that statistic gonna have a normal distribution. Right. Okay, so now this is like when n is 15, you can see that again the mean of all the sample mean is something again close to 3.5, but standard deviation is not close to the population standard deviation because it should be 1.71, but this is 0.44. So it means that whereas the mean of the sample mean, right, it close to the true the true mean, the population mean, standard deviation is not. The standard deviation actually decreasing. Okay. Because the SD should be 1.71. Okay. So the mean of y bar is not the same as the population mean. It's the same as the population mean, but the variance of y bar is not the same as the variance of the population in this case, or in any case actually, right? So central limit theorem is that the sampling distribution of the mean of a random sample is going to be approximately normal for a sufficiently large sample size. So when like you can see that when n is 15, it's more normal, closer to normal distribution than when n is 2. Right? The larger the sample size is, the more closely the sampling distribution of y bar will resemble the normal distribution. Now, if the population is normal, then y bar is normal for sure. If the population is not normal, so as you see the population is not normal, it's just discrete with 6 possible outcomes, but the sampling distribution of y bar will be approximately normal when n large enough. How large is enough? Sometimes like even 30 is already large enough. So as long as you collect 30 or more observations, you can be sure that your y bar can have a normal distribution. Okay, and as we have seen, right, the mu of y bar is the true population mean, but what I haven't shown you is that the variance of y bar is the population variance but divided by n. So that's why when n increasing, we observe that the standard deviation of y bar keep reducing, because as n increasing, the standard deviation of y bar is reducing. And so that we already talked about that when y, even when the population distribution is not normal, y bar is approximately normal for large enough n. Okay. So so this is a proof, but I'm not gonna go into that. If you want, you can have a look. This is a proof why the mean of y bar is equal to the population mean, and this is a proof why the variance of y bar is equal to the variance of the population mean divided by n. Okay. But the key thing is that we know that y bar have a normal distribution. So if we subtract y bar with its mean, which is the mean of the population, and divide it by the standard deviation of y bar, which is sigma divided by the square root of n, we're going to have a sad distribution. Okay? So and we can use that. We can use that to do some calculation. Okay. So we talk about y bar has normal distribution. Right? And we talk that mu of y bar is the true population mean, and the variance of y bar is population variance divided by n. So because y bar has a normal distribution, we can use SAT table, but we have to SAT equal to y bar minus the mean of y bar and divided by standard deviation of y bar. The mean of y bar is mu, the population mean itself. The standard deviation of y bar is the square root of the variance of y bar, but the variance of y bar is population variance divided by n square root. So the square root interact with the sigma square, you have sigma, and n here interacted with the square root, which is square root of n. Okay, so that's why SAT distribution can equal to y bar minus mu and divided by sigma divided by square root of n. Okay. So the only difference that we have seen is that the SD, right? When we talk about the distribution of y bar, the SD have to be the population standard deviation divided by the square root of n. So let's see how we can use that to our problem, to solve some problem. Okay. So here. Okay. So two more examples and then we done. Okay. So let's look at this question. Like foreman of a bottling plant had observed that the amount of soda in a 32-ounce bottle is actually normally distributed random variable with a mean of 32.2 ounces and a standard deviation of 0.3 ounce. Right? So, and the question wants us to answer this question. If a customer buy one bottle, what is the probability that the bottle will contain more than 32 ounces? Okay. So, what does it mean? Okay, let's collect the information first. Okay. So the information is that you're interested in Y, right? Y is the amount of soda in a bottle, right? Soda in a bottle. Right? So the question asks, the question gives you that the mean, the population mean of Y is 32.2, and the standard deviation of Y bar SD of Y, is 0.3. Okay, and it asks you like, what is the probability that the bottle will contain more than 32? So it asks you what is the probability of Y if you buy a soda. What is the probability that amount of soda in that bottle it can be more than 32 when the mean is 32.2 and standard deviation is 0.3. So it wants you to calculate that given that Y is normal. Okay. So when you want to calculate that and you know that Y is normal, what you can do is you can change Y to Z. This is not new. This is what we have learned from the normal distribution, right? So we say that, okay, the distribution of this is going to equal to the distribution of Z, which is Y minus mu, and divided by the SD, which is this symbol. Greater than 32, have to minus the mu, which is 32.2, divided by the standard deviation, 0.3. So we can change from Y to Z, and the number have to be 32 minus 32.2 divided by 0.3 is minus 0.67. Okay. So if you want to know that, what you can do is you can open a SAT table, right? Go and look at the SAT table, and the SAT table that we have only tell you the positive, right? So what we want here is we want minus 0.67, right? And we want to be greater than, so we want this area. Okay. So in the table, however, it can tell you the upper tail area of positive number 0.6, right? So you can know only red, but you want to know green, right? However, the red and the blue will be the same because of symmetry, right? So if you want to know the green, right? If you know the blue, the green will be 1 minus blue. 1 minus blue going to be equal to the green. Now, because we know that red and blue is the same, so you can replace that with red. So if I open the stat table, right, at 0.67, I'm gonna get that red area, you can have a look, right, is 0.2514. So the answer will be equal to 1 minus 0.2514, and the probability will be 0.7486. Now, that is this here. Okay? So, this is what you have seen before from the normal distribution. There is about 75% chance or 74.86% chance that you're going to observe a bottle of soda that contains more than 32 ounces. And you can see that if I use, if I'm going to calculate using R, it has to be P norm. So we have minus 0.67, right? 0.67, mean 0, SD1 because it's standard normal. This we want the upper tail, right? We want something more than 0.67, so the lower tail has to be false. And you can see that I have the same number over there, right? Or in R, you don't have to stick with standard normal. You can use the true normal distribution, mean with 32.2, SD 0.3, and you put 32 here, lower tail to be false, and you can see that this is, well, it almost the same number. Because this, right, this, the way we calculate, actually it has to be 0.666667. So I only put 67, so it rounded up a bit. But if you put 0.6667, you can find something close to the same between these two commands. Right? But now, what the new thing we learned is this. Okay? Foreman of the bottom plant, again, observe the amount of soda in each 32 bottle is actually normally distributed with mean 32.2 and SD of 0.3. So this is the same as before. Now, look at what changed. If a customer buy not one, but four bottles, and what we want to know is, what is the probability that the mean, the sample mean of the 4 bottles will greater than 32. So you can see that now, according to this, we're not interested in the distribution of Y, but we're interested in the distribution of sample mean, Y bar, when N is 4. Okay? So we want to know P of Y bar greater than 32 when Y is normal distribution. So when Y is normal, it's guaranteed that Y bar going to be normal distributions. If not, if the sample size is big enough, it's going to be a normal distributions, right? So mu, the population mean 32.2, the standard deviation, population standard deviation 0.3. However, right, Y is normal, so Y bar will be normal, and the mean, population mean of Y bar will be the same as the population mean, so it's going to be 32.2. However, the variance or standard deviation of Y bar is not going to be the same as standard deviation of the population. It will be equal to the population standard deviation divided by square root of n or the square root of 4. Right? So 0.3 divided by square root of 4 is 0.15. So because what we learned in the sampling distribution is that the distribution of Y bar is normal, but the variance will be different. So you have to know when you can use straight away the population standard deviation, or when you have to divide it by square root of n. Depends on whether the question want to know y or y bar. If it y bar, the formula for the standard deviation have to be like this, right? So that is the only difference. Now, so if you calculate, right, again, we want p of y bar, not y, greater than 32. So we change it into the z, right? So we minus the mean and divided by standard deviation of y bar, which is 0.15, not 0.03 now. And we observe that this probability will be the same as the probability of z greater than minus 1.33. Again, this is like 1.333333, but I shortened to just 2 decimal places. And the answer, right, if you can, okay, I'll let you check by yourself. If you use the table, it's going to show you that the probability of z is 0.9082.